So I'm happy the room is still full. I hope it's still full until the end of this lecture. I will use slides today because there's still a few things that I want to cover, and I think we wouldn't have time to finish on the boards. So if at some point I'm too fast, just slow me down, please. And before I get started, does anyone have a question or comments from yesterday or the days before? All right. Okay, so I want to start first just reviewing some of the stuff that we talked yesterday, a little bit faster, just because I also will change the notations from what I was using, so I will tell you the differences. So as we were discussing, we are interested in understanding area loss, and for pure states now, and we focus in one dimension, which is where we know something, right? So the setup is just that we have a chain of spins, then we have a quantum states on this chain. Then we have two regions, X and Y. Before this was X complement, right? Like X dash, now I'll call it Y. And we can look, for example, at entanglement entropy, which is just the von Neumann entropy of X, or we could use S max as we did previously. And then we see area law holds true if for every partition, doesn't matter what's the size of X, the amount of entanglement is always upper bound by a constant, right? Independent of the size of X, okay? So this is one concept that we saw. Another concept that we saw is decay of correlations, right? Clustering or exponential decay of correlations. So this is again defined, you could define in any dimension. Let's focus in one dimension here in this lecture. So we have a quantum state, psi. It's on n spins. And then we break up the lattice into three parts now, x, y, and z. Okay, and y separates x and z. And the size of y, let's call it L. So we saw the definition of this correlation function, right? It's the correlation, for example, between the region x and the region z. And how we define, we just take maximum over all operators m and n, for which the operator norm is smaller than 1, where m only acts on the region x, n only on the region z. And then we compute this, right? So it's the covariance, right? It's the covariance of these two observables. And then we say that the correlations decay exponentially if there is some constant that we call correlation length, psi, such that for all three regions that we choose, doesn't matter how we choose these three regions here, the size of x, y, and z might change. As long as y, the size of y is L, the correlations between x and z, which are two regions separated by L sites, this is exponentially small. In the separation, L divided by the correlation length, psi. Okay, is that clear? Okay, so then I gave you some arguments why we should intuitively expect to have area law whenever we have decay of correlations, right? And I gave you first one very simple one that is not what we should do because it's not the way entanglement works, right? We cannot break entanglements into the entanglement of x with small parts of y, of z. And then I show you this other one, right, which was a little bit more elaborated based on like Ullmann's theorem, right? So let's see how it was. So we have x, y, and z. And then suppose that the state has exponential decay of correlations, okay? With correlation length psi. So this psi EDC means exponential decay of correlations where the correlation length is psi. Okay, so the correlations are very small. So we can think that in some sense the reduced state on xz is close up to this arrow that comes from the correlation length to the reductions, right? To rho x here tends to rho z, right? And then we saw that if we only have this in this covariance measure, right? But suppose we had this in trace norm. Then if we had in trace norm, we saw that there exists this useful thing called Ullmann's theorem that allows us to write the original states, which is a purification of rho xz, right? So we can consider any purification of rho xz that we want, and we consider psi, which is a purification. This has to be approximately equal to any purification of rho x that we want, and this we just choose some local, any purification of rho x tends to rho z that we want. And we can break choose a purification, which is a local purification for x and a local purification for rho z. This is pi here and v. Okay, so y1 is just some purifying system for rho x, and y2 is a purifying system for z. And we saw yesterday, that there must be some isometry relating these two guys, right? This U is isometry. It just maps the space y1, y2 into y. So if you had a picture, x will only be entangled with a subsystem of y, and z only entangled with a subsystem of y, right? So all the correlations, all the entanglement of x with the rest is really only concentrated here on y, right? And this is exactly the idea of area law. But then we also saw, right, that this argument doesn't work. Well, first, technically, because if you really want to apply this Ullmann's theorem, we have to use one norm, right? That we saw this is the definition, or some expression for it. And here, the covariance, we only have products, right? Product operators. So this is why we cannot apply this directly. Then we saw that this is the reason why this argument doesn't work is more fundamental, right? It's simply the kind of that if the correlations between if the covariance of a state is small, doesn't mean that it's close to product in trace norm, right? It might be very far away. So this covariance is much weaker notion of correlations than trace norm distance to products. And these kind of states that we call data hiding states, they show this very well, right? So I show you two examples. One was this antisymmetric Werner state. So it doesn't matter what it is, it's identity minus the swap. But only matters that there exist these states for which the correlations between A and B, they are like 1 over local dimension, right? This state lives on CD times CD. But if you look at the distance of the state to the product, it's almost half, okay? So there's a huge gap here. So even more to the point, right? So we can consider just like random states from the Haar measure. I show you how to pick them. And then suppose we choose the size of x equals the size of z, and then y much smaller in the middle of length L. We can do some calculation again. The correlation between x and z, oh, this is a mistake. This should be z instead of y. Okay. So the correlations between x and z are smaller than roughly 1 over dimension of p, which is, right, 2 to the minus L. Because we saw that, we say that y has L qubits, but the entropy, is almost maximum, right? The entropy, so x and y, they have the same size, so the size of each one of them is n minus L over 2. So the entropy is almost maximum, okay? So just because we have a fixed state, and we have small correlations between x and some region z with some small y in the middle, doesn't mean anything, right? Yes. What do you get, sorry, in?
Non-exponential decays, because it depends on the density of states. Random states.
Yes.
Won't you have some kind of density of states?
Well, no, it's just one state, right? It's not about a family of states. So, this is a measure of quantum states. We select one of them, and we see the properties of these particular states that we get. Okay? And with very high probability over the state we choose, it will have this property. The correlation is small, but the entanglement is big. Okay? All right, so then this was, right, this sounds like a problem to us, but then I mentioned that nonetheless people, you can prove area law first for ground states of local Hamiltonians if there is a gap. And the later result I told you was this, that I want to show you in this lecture, that if the state has exponential decay of correlations with correlation length psi, then there is an area law, right? Even for S max. So this is the error. If you want an error exponentially small, this omega is just some constant, okay? Think as some constant. If you want error exponentially small in some parameter m, you pay a price of m here, okay? So, the details doesn't matter. You can think just in terms of phenomenon entropy as well if you want, just with this error term. But we already saw this yesterday. Okay, and then another thing that I show you just to try to, to build some more intuition is again, let's consider random states, right? And these are the properties that I just show you from them, right? If you choose, size of x, approximately size of z, the correlations are very small, but the entropy is very big. So this is bad for us. The conclusion is that if you have small correlations in a fixed partition, this does not imply area law, right? We have to do something else. But we can move this partition the way we want, right? That's the main point, right? So if you have exponential decay of correlations, not only x and z has small correlations, but if you just change the size of these regions, change the way we define them, we must have small correlations again. So this counterexample just shows that if we want to prove the theorem that I mentioned, we have to consider this decay of correlations in many cuts at the same time, right? We have to move these regions and use that all of them has, the correlations decay fast in all of them, and then get the results. So let's do this. Let's just do this trick of moving the size of the regions for random states, okay, and see what we get. So suppose now that the size of x combined with y is smaller than the size of z. Okay, so now z is very big. Now what I show you, right, last lecture, just using that the entropy of this is very big, and Pinsker inequality is that actually these states on xy, rho xy, it's very close to the maximum mixed states, right? So tau x is the maximum mixed states. This should be dimension of x. On x, tau y is the maximum mixed state on y, and this guy is very close to this product maximum mixed state. So this is some jargon that we use in quantum information theory sometimes. We say when we have a bipartite state which is close to a product state, we say that one subsystem x is decoupled from the other y. Okay? So in this situation we have that x and y they are decoupled, right? So as we know, we have extensive entropy on x and y and on x itself. But actually this implies that we have a lot of correlations, right? This was one of the last things that we saw. Why? Because of Ullmann theorem, right? So we can consider again this trick of purification. So we can purify x here just with z, some subsystem of z, and the same thing for y. But then, because x is maximally entangled, maximally mixed, x must be maximally entangled with some part of z, right? So there is some unitary. We just do a change of basis in z, and then we get that x is maximally entangled with a subsystem z1 and y with another one. But maximally entangled state has a lot of correlations, right? You just measure coincidence, for example. So we saw, right, that this implies that the correlation between x and z, they are very big, right? They are of order 1 for a separation y, which can be of order the system size, right? So random states, we don't care about them because they have long-range correlations, right? But this is already interesting, right? Because it shows that, as I showed you yesterday, from the assumption that the entropy here is very big, almost close to maximum, we get that this state is almost decoupled, and then we get that the correlations are long range. So assuming that the correlations are not long range, we can get that the entropy of xy cannot be maximum, right? It has to be bound away from maximum, which is something in the direction that we want, right? So this reasoning hints at the idea we want to do for the proof, okay, that I want to explain. So we will show that that's a funny sound. The large entropy leads to large correlations. Okay, so this will be the strategy. So we assume that area law doesn't hold true. So we have some regions of very large entropy. From this, we wanna find that the correlation must be big as well. And because we know the correlations are not big, our initial assumption cannot be true, and we must have an area law. Okay. So the way we're going to do that, we're going to try to show these correlations by doing a random measurement on some, like here on A, in such a way that after the measurement, A is decoupled from B. Okay. So this is what I want to. You'll be much clearer now. So how we do that, we start studying these entanglement distillation protocols. Okay. So this Graham talked about just before the break. I started introducing it last time, but probably there wasn't time for you to get it. It was very fast. So let me mention again the important points here. So this, this entanglement distillation appears in the problem when we have two parties, here Alice and Bob, and they have some states, some entangled states, okay? Like rho AB, for example. And they would like to do some local operations here and here, and it communicate classically, and distill from these states some EPR pair, right? So I already wrote it, but let me write again, right? So the goal is to start from rho AB by LOCC to get some copies of a maximally entangled state. Right? This is the EPR pair. So now two interesting questions is first, given these states, rho AB, they said he's just the AB reduction of psi. Given this guy, this is just a purification, okay? You have this state, but of course you can always purify it to some state psi on some environment. So given the state rho AB, we want to understand first what's the maximum number of copies of EPR pair that we can extract from it, right? So this is the distillable entanglement that Graham introduced. Another parameter that we're interested is how much classical information Alice must send to Bob and vice versa, right? So how much they have to communicate to implement this transformation. This is the classical communication cost of the protocol, okay? And then, of course, we would like to find protocols that optimize these two things, right? We want to extract the maximum number of EPR pairs possible using the minimum number of communication possible. And then, there's a lot of study in entangled distillation protocols. In general, it's a hard problem, but we know some interesting things. So this is one result that we're going to use by Rodesky, Oppenheim, and Andreas. So given a state, psi, AB, like here, Alice can distill this number of EPR pairs. So this is minus the conditional entropy of A given B. Okay, if you want to write it, it's just S of B minus S of AB. This number of EPR pairs with Bob, using a very simple protocol. Okay, so of course this general protocol can involve measurement here, communication again, infinitely many rounds if you want. Can be very complicated, but this protocol is quite simple. So Alice just makes a random measurement on her system. I'll give you the details in the next slide, with this number of elements, okay? So the number of elements of the measurement is exponential in the mutual information that we saw before between Alice and Eve. So this is the definition of the mutual information again. And then she just communicates the outcome. So she makes this random measurement. She gets one of n possible outcomes. She communicates this outcome to Bob. And then Bob just applies some quantum operation. And after this, they have a EPR pair, okay? This number of copies of EPR pair, or very close to that. So one important thing is that this what I told you is true, but it only works when psi has this form, okay? It's a IID state. There's many copies of a particular state, and n is very big, okay? So then this is a theorem, but now what I want to do for the next half hour is just to cheat a little bit and just pretend that it works for one copy, okay? And because this will simplify things a lot. And then later we will see how we handle this. And we will handle this just by using results very similar to this one, but where instead of having these nice entropies, right, like von Neumann entropies, like max entropies, like the entropy that I showed you before, we must change here the rates, right? Because then we know that it works for one copy. Any questions? Yes? So, right, the distillable entanglement of the state rho AB is always bigger than this, okay? Always bigger than SB minus SAB. This is called the hashing bound, but.
And the protocol you are saying they are using only one way.
That's correct. Yeah, because it's right. It's even very simple, right? So the measurement on Alice is always a random measurement with this number of elements. So she makes a random measurement, get one of possible capital N outcomes, communicate this outcome to Bob, and he does something conditional on this outcome. That's right. So yeah, because I don't need it here, I'm not mentioning, but this protocol achieves more than entanglable distillation. It also merges Alice part of state to Bob. Okay, but I won't get into that. Okay, yes.
The EPR states which will be generated due to distillation.
I'm sorry, can you? I didn't hear.
EPR states which will be distilled, that will be in Alice's side, not shared EPR state.
Oh no, so EPR state is between two parties, right? So the EPR state will be between Alice and Bob, right? They will share this maximum entangled state in the end. This is just really because we want to consider to relate to area law. We want to consider pure states, right? So I'm just relating this entanglement distillation protocol to properties of tripartite states. But so far, this E does nothing. It's just some purification of the states. Okay, it's completely passive in the protocol.
So initially they share one copy of psi or more than one?
Right. So what I told you here, this will only work if the state psi that they share is actually of this form for n very big. Okay, so many copies of a particular state. Okay. Later we'll see what's the analog of this when they only have one copy. Okay. But for now, if you want to, everything that I wrote here is correct if psi is of this form. But now, for the moment, I want to just pretend that it works for one copy as well, right? Just to simplify things. So as I mentioned, how the protocol works. It works by applying a random measurement. So these pk, they are the elements of the measurement. Okay, so it's von Neumann measurement. So we know it's a measurement, so these pk's, right, just to remind you, they are a resolution of identity and they are orthogonal, right? So they are projectors and they sum to identity. Okay, and this acts on Alice space, right? So how it works with more equations. This is the action of Alice's first measurement, right? So she maps the state psi to a state phi, where they are depending if she obtains outcome k. This is the new state, right? We just project k onto the states up to normalization. We have to renormalize to be a unit vector, right? So after the measurement, she has these states if she obtains outcome k. Now, how this works? So let's use this idea of decoupling again here, okay? Which won't be essential for us, but it's interesting to see how this works because this is very useful in many other contexts. So she does this measurement, and now the only thing that we will ask from the measurement is that this holds true, okay? That if you look at these states, phi, A, B, E, now we trace out B, we trace out Bob, and then we have this state phi, A, E. The only property that we want from these states is that if you look at the trace norm between phi AE and a state, which is a product of a maximum mixed state on A, so this is the maximum mixed state on, this new A, they might have a different dimension from the original A, right? Because we apply this projector. So we have a maximum mixed state in this subspace of the original A, and we have the original reduction on E, okay? Phi E is just the reduced state here on E. Suppose that after the measurement, on average, at least over k, this is true, okay, or very close to 0. Then the claim is that they can achieve entanglement distillation, okay? So let's see this in a few seconds. But first, what these guys proved, Andreas with Michal Horodecki and Jonathan Oppenheim, is that you can find these pKs which achieve exactly that if the number of pKs or the log of the number of the pKs is this mutual information. Okay, so the number of pKs that you need is of order exponential in the mutual information of A and E, right? So, so what we do, we are doing is just that we have a space, the space of A, right? And then these projectors, you can think just getting some subspace here, right? This is the one associated to P1, P2, etc. So they just partition the space into n subsets, okay? Where n is equal to exponential in mutual information of A and D. So they prove that choosing this number of pKs, this will be true, and the dimension of this A dash, right, which is the dimension of A after this projector is applied, or in other words, it's just the dimension of each one of these pKs, is equal to, the log of this dimension. This is dimension, okay? There's a different notation here. Is equal to SB minus SAB, which we saw, right, will be related to the EPR, how many EPR pairs you distill in the end. Right, So now, why this is useful? So let me show you. So this is exactly, yes.
So this should hold true for all values of k or
For most of them, it's enough.
for
Okay.
most of them?
For most of them, yeah. So, or even if this is just on average over k, very close to 0, it's fine. But, okay, so now why this is what's interesting? Why this is enough for us to distill entanglements? We already saw this, right? It's exactly this this Ullmann trick again, this decoupling again, right? But let me just write it one more time because it's something that is very good to know. So we have Alice, Bob, and Eve. They share these quantum states. And now what we are saying is that after the measurement, these are the states that they share, right? And we are saying that A and E, they are close to product states, right? But now one purification, so let's look at this reduction rho AE, phi AE. These are approximately products. Good, but then we can apply this trick from before, right? So we can consider any purification of this guy that we want, and for this guy we choose this purification, the original state. Now we can consider any purification of this guy we want, and now for this one we just choose some local purification, right? So this is close to maximally mixed, right? So a purification of this guy is a maximally entangled state between A dash and A prime. Some local purification. A purification of this guy, well, doesn't matter what it is, but we can just choose any one we want, right? So it will be E prime, okay? And now we know that just operating on Bob, right? So we know that applying some isometry to B, we can recover the original states, right? Or let's do the other way. This is equal to the original states. This is exactly what we saw yesterday, right? With some isometry on B, okay? Where you map B to this isometry, maps B to A prime, E prime, okay? So if Bob just applies this isometry here, he applies it, and after he applies, they have these states, okay? But now Bob has these two subsystems, right? Bob has, after this isometry, he will have both A prime and E prime. So it means that he has maximally entangled states with Alice, right? They share this state now. Bob has this A prime register. So this, so they have distilled entanglements. The question about state merging, you can prove that, this is just any purification of phi E. So this must be equal to these states, to the original states up to some local change of basis on A prime, okay? But this doesn't matter, okay? So it's the same thing again that we saw. Because of the coupling, we have entanglement distillation. Right. But what we care here, this is, I want to show you because it's related to this random state and it's something nice to know. What we care is that there exists an entanglement distillation protocol with these rates, okay? This number of classical communication, number of bits communicated from Alice to Bob, distilling these rates. Right. And now what I want to use is just to argue that this entanglement distillation protocol implies some useful relation between entropies and correlations, okay? And this is the relation. So first let's see the relation, and then we see how it follows from what I told you before. So again, we have a states, x, y, z's. So this is just to make connection with entanglement distillation, but this is our original chain, right? So we associate A with X, Bob with Z, and Eve is in the middle, the purification. So now what it says is that if the entropy of Z is bigger than the entropy of Y, right? So this is, in the end, we want to use this as saying that suppose there is no area law for Z, right? So this means that the entropy of Z is much bigger than the entropy of Y because Y is constant sized. Then we can get a lower bound on the entropy between Z and a faraway region X. Okay? And this we want to relate to, of course, decay of correlations in the end, right? But what are the numbers? If the entropy of Z is bigger than the entropy of Y, the correlations between x and z, they are bigger than some constant times something exponentially small in the mutual information between x and y. Okay? So here you have z and y. Here you have the correlation between x and z. And here, again, the mutual information between x and y. Okay? So these will be the three relevant things. And then the proof really that I'm going to show you next is just about choosing each time different regions and applying this inequality over and over again. Yes? Okay, this is what I'm just claiming that it follows from entanglement distillation. Okay, it's not clear why it follows yet. But it just says, right, if the entropy of z is bigger than the entropy of y, the correlations of x and z, they must be bigger than something. Let me show you how this follows, yes. Okay, so let's rewrite this, right? So this is the same thing as saying that entropy of z minus entropy of y is bigger than 0. Okay, so maybe let me give some more details. So what we have here is entropy of z bigger than entropy of y. So this is the same as entropy of z minus entropy of y bigger than 0. But now you have to remember that the state psi is a pure state on x, y, z. So because of this, the entropy of y is the same as the entropy of xz, right? For any bipartite pure states, the entropies are the same. So we can replace it here, and we get that the entropy of z, which one I want to change? Yeah, this one. Minus entropy of xz, this is bigger than 0. Right? But now, this is the rate of EPR pairs that we can get in entanglement distillation, right? Because we are identifying Alice with x, and we identify Bob with z, right? So if you remember from what I show you, this was the rate, SB minus SAB. Now, A is z, so this is SA, and x is A, and z is Bob. So this is SAB, okay? So if we would run an entanglement distillation protocol between Alice and Bob, as long as this is true, we could distill one EPR pair, right? So this condition is just saying that Alice can make a random measurement here, communicate something to Bob. Bob can apply some isometry, and then they will have at least one EPR pair, right? They might have more, but at least one, okay? So this is just saying that entanglement distillation is possible here between Alice and Bob. Now, suppose they just run the entanglement distillation protocol and they get this EPR pair, at least one. They can measure this EPR pair, as we saw yesterday, and get correlations, and get like constant correlations, right? So because of this condition, they could run the entanglement distillation protocol and get 1 bit of correlation. Or, I mean, the correlation non-negligible. So this, maybe you think it would suggest the correlation between x and z is bigger than some constant that we get from the EPR pair. But the problem here is that they can only extract this EPR pair if they communicate, right? They have to send classical bits to each other, from Alice to Bob. And correlations, in this definition of correlation, there is only local measurements, right? So we have to pay for this classical communication somehow, right? And then the idea here is that there is the following relation, okay? So it's something that I will discuss with you maybe in the problem session if you're interested, but let me just state is the following. So if there is an entanglement distillation protocol, so if you have rho AB, if from rho AB we can extract 1 bit, can distill at least, right, but maybe more, 1 E bit, 1 EPR pair. with C bits of classical communication, then the correlation between A and B, it must be bigger than 2 to the minus C, roughly. Okay? So it means that this idea that you can extract the API pair and therefore you have correlations is true, but you have to pay the price proportional to the classical communication. Okay? And if you maybe we can discuss this more later, but let me just write one more thing. So why this is the case? Because in a grammar already wrote, right, and you see next week in Eric's lecture, but the way to describe this entanglement distillation protocol, because the communication is one way, is as follows. So this is the operation. This is AB. And then we can always write this as let me write, let me write like that. Some AJ, MI, and IJ. Sorry, it's better like that. Where this I goes from 1 to 2 to the amount of classical communication. Okay, so what's the meaning here? This is the measurement that Alice does. Okay, so she makes this measurement. Right, so this is just some POV measurement. And then after she makes this measure, she communicates I to Bob. And then Bob applies this decoding operation. Okay, so this operation is really just some isometry. And the thing that we know about these states is that after this operation, after we apply it, we have a API pair between Alice and some subsystem of Bob. Okay, so one way to do it is that if you trace out some part of Bob, we get API pair. So now this is good, right? Because if you just look at each one of these terms, okay, if you just look at one of these terms, because on average they are close to phi2, what you can prove, and let's discuss this in the afternoon, is that for many of them, just each one of these terms, they will be also close to phi2. But if you just have one of these terms, it's very good for us now because this is just some local action, right? So this cannot increase the correlation between them, okay? So you can just see that if you just apply this, the correlations can only get down. So it means that for one of these terms, the correlation will be big as well. But we have to renormalize the states. And the trace of each one of these guys is of order 2 to the minus C. Okay? So this is this relation. Don't worry if you didn't get it, we can work this out in the afternoon. So this comes from the fact that they can distill API pair, and we have to pay the price of the classical communication. Okay? So this is the probability of getting each one of these 2 to the power of mutual information of X and Y outcomes. Because the measurement is random, they are roughly with the same probability. This helps. And therefore, we have this bound. Is there a question on this? OK. So if you got lost on this entanglement distillation, don't worry. You can just forget about it. This is the relation that matters. Okay? It's just some relation that we can prove by entanglement distillation between entropies and correlations. So now let's see how we can apply this relation to prove the result we want to prove, right? So we want to prove that from exponential decay of correlations, we get area law. Okay, so we want to do this. We will do this in 3 steps. Oh yes, please. Yes. Oh yeah. This or the before? Yeah. Well, no, they are random, but there is a condition on the number of them, and because they are orthogonal, this puts a restriction on the size of each one of them, right? So you must take PKs. They are just random projectors. Is a random measurement, but the dimension of each one of these PKs is equal to 2 to the power. The log of the dimension of them is equal to that. That's the only constraint.
But if by that relation I just constrain their number,
Right.
they are equivalent of some unitary transformation.
Oh, no, sorry. So, I mean, the number is fixed, but you also require that all the dimensions of them are the same. Okay? So, more concretely, let me write this concretely, because, okay. And then you define this QK. This will be sum, or let's define it. Q1 is sum K from 1 to N over, to dimension of A over N of the computational basis. Okay, so the first dimension of A over N elements of the computational basis. Q2 would be the same thing, but K runs from this up to 2 dA over N computational basis, and so on. So really, we just partition, all the space into subspaces of the same dimension. So of course, this is for a fixed base, the computational basis, or any basis you want. The definition of the P case is just that the PK is equal to some unitary applied to the Q case. Where this unitary, the fact that they are random just means that this unitary we take from the Haar measure, okay, on the unitary group. So this is a more concrete way of taking these random measurements. You can always think of this procedure, okay? Any other question?
For doing this distribution protocol, there is a back and forth, multiple back and forth communication between Alice and Bob.
Then it's not simple like the way I wrote, right? Then it becomes more complicated, right? This is only because there is only a measurement of Alice. She communicates something, and Bob just do some decoding operation.
Oh, okay,
So right, so he just change the basis, and then the APR pair will be there in some subsystem. So he just has to trace out the trash, right? If it was back and forth, then we can write something like this, but it gets messy because you have to, right? Okay, so how we want to do? We want to do in 3 steps, okay? One builds on the other, and each one of them they are simple in itself, and they all use this relation that I show you between entropies and correlations. So one is to prove that we can get an area law from this assumption of exponential decay of correlations, that there is a correlation length, under some assumption that there is some region of subvolume law, okay? And I'll tell you what this means, of some subvolume scaling of entropy. Then we'll be done with this. Then we'll show that how to find this region of subvolume entropy. We'll show that we can get a region of subvolume entropy from the assumption that there is some other region of small mutual information, okay? And finally, we'll show that we can always find a region of small mutual information. So this proof works for any state with exponential decay of correlations. But to simplify things, let's think that the state is translation invariant. Okay, so you have a state, and if you just translate this guy here, this guy here, this guy here, we get the same state again. Let's assume this because then we only care about the size of the regions, right? We don't care where they are, and this will simplify things, just for now. Although we don't have to use this. So let's do the first step. We want to get an area law from the assumption of a subvolume law. And we want to use this relation, right? This is the relation we just saw, how to derive. So actually it's more useful to use the reverse implication. So big entropy means big correlations. This is the same as having small correlations implying small entropy, right? So this is just another way of writing the result we saw. And now this is our assumption. Suppose that we have x, y, and z, but the entropy of y is smaller than L over 4 correlation length. So what's the maximum value of Sy? For, what's the maximum value the entropy of y could be? Who knows? Right, and here it's qubits, and y has L qubits. L, right, L, yes. Right, so the entropy of y could be at most L. Here we're saying that is a little bit smaller than L. It's like L divided by some constant, okay? So this is what we call this subvolume law assumption, right? So we're just bound away from the maximum value. We can still be very far away from area law, but we are bound away. And we want to show that this assumption implies an area law for Z, okay? So Z, we have no restriction on the size. Y can be any size, but suppose that this L is like of order correlation length is small, then we can get area law for Z. How we do it? It's very simple. So we look at if you want to apply this result, right, you have to compute three things. We have to compute the mutual information between X and Y, or at least bound it. We have to try to bound S of Z and S of, okay, this we don't know, but this will be our result. But this we have to try to bound somehow, right? So let's do it. The mutual information between X and Y, one property, right, that we saw before, is that this is always smaller than twice the entropy of Y. And the same thing will be true for X, but let's use this relation. But now, Y, right, let's use our assumption on Y. The entropy of Y is smaller than L over 4 xi. So times 2, we just found that the entropy of X with Y must be smaller than L over 2 xi. Okay, so we have a bound on the mutual information of these two regions, X and Y. This is on one hand, we have this. On the other hand, we can also get a bound on the correlations, right, between X and Z from exponential decay of correlations, right? So the correlations between X and Z, they must be smaller than 2 to the minus L, the separation, over the correlation length, right? Because the state has exponential decay of correlations. This is the kind of states that we care. But good, so use this relation. So identity, the mutual information is smaller than L over 2 xi, so therefore this is true, right? So how you see that? Well, so you forget about the 2 here, this minus, so we reverse the inequality, so mutual information is smaller than L over xi. So fine, right? It's even smaller than L over 2 xi. So we just found what we want, right? So we found that the correlation between X and Z, these two regions far away, they are smaller than the mutual information between X and Y, okay? And this is very good for us, right? Because we just apply our little result here. So because this holds true, we also find that the entropy of Z is smaller than the entropy of Y, right? And Z, Y can be something of constant size. So if we have a region small enough which has subvolume law, we get area law, right? We start from some assumption about the entropy only on Y, and we get a bound for the entropy of Z, which can be something much bigger, okay? Does anyone have a question on this? Yes. Right, this is the assumption we are using, right? By subvolume law, I just mean that there exists a region Y such that this is true.
Does that subvolume law constrain the correlation length? Its max is L by L.
Yeah, right. I'm assuming that there is a state which has exponential decay of correlations with correlation length xi, and moreover, you can find some region Y of not so big, like think of constant size, for which this holds true. Okay, so this is some extra assumption, right? Now, of course, what we have to do is to get rid of this extra assumption, but this we're going to do just now. Okay, so is this structure, right? First, we prove under this assumption of subvolume law. Then we remove. Now I will show you this subvolume law assumption, and replace by another assumption, namely that there is a region of small mutual information. And finally, we show that this assumption of small mutual information is always true. Okay, so putting everything together, we have area law always. Okay, so this is what we want to show now, right? That we can prove that the region has subvolume law from some other assumption that I will tell you what it is. So this is the assumption now, is small mutual information. So now we have our lattice. And again, it doesn't matter what these regions are. For here, right, assume translation invariance. Just so you have one thing less in your mind. So now suppose we want to prove that this region YC has subvolume law, okay, in the sense that I defined before. So we just have some YC of some fixed size, L, and we want to prove that it has the entropy is not maximum. So what's our new assumption to prove that? We will prove that whenever we consider a region composed of YC, the region we care about, and some boundaries, Y left and Y right, and the boundaries, the length is L over 2. So we consider this region, and we look at the mutual information between the central region and the boundaries. Okay? So what's the maximum value that this can take? Who knows? The mutual information. So this is the mutual information between a region of L qubits and another region of L qubits. 2L, right? Exactly. So here we're saying this could be at most 2L. We are saying that it's a little bit less than that. It's L over 4 psi again. Okay? So this is what we call this small mutual information assumption. So let's see again why, if this is true and the state has exponential decay of correlations, this implies that the entropy of YC must be small, like subvolume law. Again, the same kind of idea, right? So we have exponential decay of correlations first. So let's look at the correlations between the central region and R. R is all the rest, right? R is what we obtain if we look at all the lattice and we trace out YC, Y left, YC, and Y right. So the correlations between YC and R, first, these two regions, YC and R, they are separated by L over 2 sites, right? Because this is L over 2 and this other one is L over 2. So it means that by exponential decay of correlations, this is smaller than something exponential in L, minus L, and 2 psi, right? Because the separation is L over 2. But what's our assumption? This is our assumption. So this means that this bound is smaller than something exponentially small in YC with Y left and Y right. Okay? And now we want to use our lemma again, right? About correlations and entropy. So I didn't write it, let me write it here. So how it was that if the entropy of, let's see, if the entropy of Z, but this is no, because let's go to the origin. Okay, sorry. So this was the guy, but let's write using Alice, Bob, and Charlie, okay? Because we are changing the to be safe. So this says that the entropy of Bob, if the entropy of Bob for state psi ABC. I'm sorry if I keep changing this because we have to redefine the region. So what's Alice in one case becomes Bob in the other, so it gets confusing. So let's rewrite this in terms of Alice, Bob, and Charlie. If the entropy of Bob is bigger than the entropy of E, ABE, right? Then the correlation between X, which is Alice, and Bob, this will be bigger than 2 to the minus mutual information of X and Y, Alice and Eve. Let's go back there and see what this implies. So this we have by assumption because the mutual information is small. Now from this distillation bound, by this I just mean this bound, okay? Let's see what we get. This is saying that the correlation is smaller than the mutual information, right? So what's YC? YC here we will identify with Alice, okay? So this implies that. So if the correlation is smaller than this bound, it implies that the entropy of P is smaller than the entropy of E. So now what we are doing, let's replace all the things here, right? So we identify Y central with Alice, okay? So whenever we have Alice, we put Y central here. So Y central, Y central. We, okay. Right, so here we have this term, right? Y central here that we want. Now, what's E? E is, what's Bob? Bob is all the rest. And E is Y left and Y right. So where we have here we put Y left and Y right. Okay? And now Bob is the rest, right? So when we have B, we put R here. Okay, so this is exactly this relation we saw before, but in this weird way of assigning Alice, Bob, and Eve. So now we have this. We have the decorrelations between YC and R. They are smaller. This should be, what was E? E was Y left, Y right, right? So here we have exactly what we want, right? We have that by decay of correlations of Y, the central region, and R, it's smaller than, this is like 2 to the minus mutual information of Y central and Y left, Y right. Okay, so this is true. This we prove is true. And therefore, by this result, the entropy of R is smaller than the entropy of Y left, Y right. So we conclude that this is true, right? But again, let's use this trick. So this is a pure state. So the entropy of R, this guy, must be equal to the entropy of the complement, right? The entropy of Y left, Y center, Y right. So we find this equation. Okay? Any question on this? Right. So we just have to shove things around and we get this relation. And now we are done, right? Because let's see. So entropy of YC, which is what we care, it's always smaller than entropy of YC plus some positive term. Why this term is positive? Because we just proved it, right? So we just proved it that entropy of Y left, Y right minus entropy of Y left, Y center, Y right is bigger than 0. Okay, so we just add this positive term. But what's this? This is just the mutual information, right, of Y central with Y left and Y right. Right, the mutual information is the entropy of the first guy, this one, plus the entropy of the second, minus entropy of the total. But again, we have an assumption on this guy, right? We know that this guy is small. We know this guy is L over 4 xi. So we get that the entropy of YC is small, it's smaller than the same thing, L over 4 xi. Okay? So this is the result we wanted, right? So from another assumption about mutual information now being small, we get that the entropy of the central region is small. Okay? And again, here we use our result from entanglement distillation and decay of correlations here, right? So in the 2 steps, we use in each one of them decay of correlations, our assumption that there is a correlation length, and this result about entanglement distillation. So now we just have to show that we can always find this region, okay, which satisfies this property. And this holds true now for any state. Okay, for any state, you can find some region that is not so big, which satisfies this. So this is something interesting, right? That for me was surprising, at least that is true. But let's get there. So it's now finally to prove area law for this region, for example, we just have to find some region. In the general case, not so far and not so large, but if there is translation invariance, just some region, we don't care where it is, of this form, exponentially big in the correlation length, okay? And this will be the final bound on the entropy, but this is a constant, right? This doesn't grow. Good. Okay, so this is just in the general case. If you don't have translation invariance, we don't need that. So let me just state the results, okay? This final result that I mentioned. This general lemma, okay, I find it very nice. It was already in Hastings' proof, actually, when you have a Hamiltonian. Not in this way, but the idea was there. It was used in his proof in a very different way that it's useful here. So at least for me, maybe there is a better way of looking at it. So I think this is a powerful result. It's worth knowing, maybe for some other application. So what it says that, okay, in general, given any quantum state or a probability distribution, doesn't matter, or any quantum states, and some site S, then for any parameter you choose epsilon is some number bigger than 0, you can find a region as the one we want, right? Y left, Y central, Y right, size L over 2, L, and L over 2 again, where L, we don't know the size of L. Okay, L we have to, there is one L for which is true. We don't know which L is true, but we know that we can bound it. It's bigger than 1, of course, and it's smaller than something exponentially big in 1 over epsilon. Okay, so there is a range of L that we have to vary, but there exists one, and the distance from S is also bounded by exponential 1 over epsilon, and we have what we want, right? The mutual information between the central region and the boundaries is smaller than epsilon L, right? Again, the maximum of the mutual information here is 2L. here for any epsilon bigger than 0, we can show that there is one region of size epsilon L. Okay? So substantially smaller than the maximum value. So this is quite interesting, right? Because there is simply no assumption on the state. This works for any state. All that it says is that if you have some flexibility in changing the size of this region and where the region is, there exists this region with this small mutual information. Okay? So let me just do one more drawing to illustrate what's the idea here. So the proof is extremely simple. I'll do it. Maybe I don't show you, or maybe I show you. It's just subadditivity. You apply subadditivity many times. But the basic idea is, suppose that we start from some region. Let me write very big. Suppose this is our original region, okay? This is like our initial y central, y left, and y right. And now we just compute the mutual information, and we find that this mutual information is not small, okay, it's big. Then what we do, we just look at regions inside each one of them, okay? Now we look at the region here. One here. And one here. Okay? And now we have these three regions, and what we do, we look at the mutual information again for each one of them. Now suppose that all of them are big again. Then what we do, we do one step more. We break each one of them into smaller regions, and we check again. What you can prove, and this, you use subadditivity many times recursively here. I think I won't do this, but I can show you later. Is that just because of basic properties of the entropy, at some points when you keep shrinking the regions, this must be true. Okay? So this says that the mutual information cannot be big on all length scales, right? If it's very big on one length scale, it has to be small on the other one. One extreme case where it's very simple to see this. Suppose that the mutual information is 0 here on the first, it's maximum on the first level, okay? It's equal to 2L. If the information, just some example for you to see what's the kind of thing. If the mutual information between y central here and y left, y right is equal to 2L, then we know what the state is. Okay, there is only one state that satisfies this. It's the maximally entangled state between y central and y left, y right. Okay, so we must have maximally entangled between this and this. So this implies that the states on y central, y right, y left is a maximally entangled state. So this is the maximally entangled state. But now what's the reduced state on yc? If the state is maximally entangled, it's just the maximally mixed state, right? So it means that the state here is maximally mixed. But if it's maximally mixed, of course, it has 0 mutual information, right? The mutual information is just 0. Okay? So if for the big region the mutual information is maximum, we find that for this smaller region it must be 0. So what happens in general is a trade-off, right? This is not maximum, but if it's big enough, bigger than epsilon L, this has to be a little bit smaller. And then we do again, and the next one has to be a little bit smaller. And then at some point, it's small enough. Okay? So this is the basic idea. Any question? Yes.
This was for any state, independent, there's no mention of the Hamiltonian.
It's any states. Yes. Any mixed states. Right. Yeah, I don't know. In his proof, he needed this for some other reason, even though he cared about ground states. But this was, if you check there, you won't see. But what he uses is just this in this guise. Okay, he doesn't talk about mutual information, but he talks about subadditivities of entropies, and it's very similar. So he found this trick, and he needed it for some reasons. But this is the only part where he uses information theory. It's here. Okay. And then, right, I think it's a very nice idea in general, right? It's just in words, the correlation, correlations cannot be big on all length scales, right? It's something very different that we usually do in information theory, right? In information theory, we have our partitions very fixed from the beginning, right? We have Alice, Bob, and Eve, and they are what they are. and they cannot change these partitions usually, right? Here, because we have this freedom of changing what are the regions we care about correlations, we get this interesting behavior. Okay. So, if with this result we are done, right? With this result we find the region of, epsilon can be anything. We choose epsilon equals 1/4 correlation length. So it exists this region. We go back here. This assumption is true, and therefore we concluded the subvolume law for the region YC. And from this argument I show you, this shows that from this assumption subvolume law we get area law. Okay. So that's the proof. It's these 3 steps. In 2 of them we use decay of correlations, right? Plus this lemma on entanglement distillation. The last one is just some general feature of correlations in quantum states, or even, this holds true classically as well. Okay, but no, we are not done, right? And we are not done because, as I mentioned, we were cheating, right? So this should be entanglement distillation, okay? So this entanglement distillation protocol, this result that I was using all the time, only works when we have many copies of the states, right? We must have a large number of copies of the same states. But in this problem we are studying, we only have 1 copy of the states, right? We have this state with exponential decay of correlations, and we want to see correlations in this state. We don't have the luxury of having many copies of it. So if you want to really make this argument rigorous, you can see I was using the slides from some other school, and Neil Angela that explained about single shot information theory. But I will be Neil Angela for the rest of the talk, and I will explain you what single shot information theory is. So if you want to make this rigorous, we have to use this very nice framework that is called single shot information theory. So what's the goal here is to do exactly what we want. Okay, we have a result that works for when you have many copies of a state, and we know, we want to use this theory. It's good for us for doing something here to prove area law. But we cannot use it, right? Because we just have 1 copy of the states. Then what you do? Well, we have to modify the theory somehow, right? And this is state merging. You can just see as entanglement distillation that we use. So we have to replace this entanglement distillation rates that I told you, which allows us to prove this, to single shots entanglement distillation rates. Okay? This is one thing we have to do. And it's good that this was developed by some people already, but we need to add something new to the game as well. And the saturation of mutual information that I mentioned, this Hastings result, we need some version for them like max entropy as well. Okay? That works for single shots. Okay? That doesn't work for this mutual information, because this won't be the relevant thing here anymore, but works for the analog of the mutual information. And this is much harder. You have to do a lot of new tricks, right? The original proof is very simple here. This one is harder. And this, I don't want to mention anything about this, okay? So, but I do want to mention now, for the rest of the lecture, at least a few, in the last 15 minutes, just a few of these modifications, right? What changes once we go to the single copy level, okay? And this is interesting in itself, right? And maybe you have some other uses in mind for this framework. So what we want to do is go beyond this, this IIT, identically and independent distributed simplification that I use in the proof, right? So we cannot use it. We have to do something better. And then, so this single shot information theory that has been very, quite successful in recent years, but not everyone is happy about it. Okay, so and we'll see why, right? So there are, I guess, 2 views of this theory. One is that it's the right information theory, right? Because this assumption of many copies, it's some abstraction, right? It never holds. In real life, we never have many copies independent, right? So, we have to go beyond this IIT. Another view, opposite view, is that it's very boring, the theory, right? Because it only gives trivial reformulation of the problems itself. And we saw an example of that, right? I introduced on the first day S-max, and we just saw that, of course, it gives the compression rate, right? But it's log of the rank of the states, right? So, there is no result here. By definition, it gives the compression rate, right? So maybe all that this theory is doing is that just getting the original problem, reformulating it in some way that looks like some entropy and say this is the right entropy. But nothing has been achieved in the middle, okay? And I don't believe in either of these 2 these two views, but it's somewhere in between, right? And this is what I want to show you very briefly. Okay, so it's a useful theory on one hand, so it's not about trivial reformulations, but it's much less useful than RID in the sense that the entropies that we have to work with, they don't have a lot of structure like von Neumann entropy has, right? So we use all these nice properties of von Neumann entropy in the proof, for example. We don't have all these nice properties anymore. We have something that look like them, but we need much more work. Okay, and this is really, I think, the take-home message from this single-shot theory. It's something in between, gives partial answers, and then you have to work through specific problems and see if it's going to be useful there or not. But luckily for us, it was useful for this area law problem. Okay, so this is, we want to prove this result, right? I already mentioned, this is the decay of correlations. Fine. Now, what are these entropies? So let me just first write some of them that we actually use. And I won't have time to give any meaning, any intuitive meaning of them. But at least I want to show you, and then you see that things that were very simple before in the asymptotic case, in the von Neumann case, they become quite messy now, right? So one thing, so what happens is that we have these entropies, and before we, this is the conditional entropy of A and B. Is there a question? Okay. This is the conditional entropy of A given B on some state rho AB, okay? So in the von Neumann case, what it will be? It will be just entropy of AB minus entropy of B, right? So some very simple expression that we used here, right? So now it becomes this, okay? So it's some optimization problem. We have to maximize over state sigma, and then we take the supremum over, well, it's just maximum enough. So maximize over state sigma, and lambda is a real number, and we look at this, okay? There's something wrong here, I think. No, that's fine. Okay. Right. So I don't expect you to read anything from this, but this is what we have to use now. Whenever we use conditional entropies now, we have to use this beast now. Okay. Now the same trick that we did for S max, we usually have to do this here. So this is not, it's a very rigid object. We have to smooth it a little bit, and then we just do this smoothing the same way we did before. We look at approximations on the epsilon ball around rho, and we compute this quantity on this approximation. Okay. Now, one thing, why they have this minimum here? Well, because one thing that always happens in the single shot is that one thing that was just one quantity before, like the conditional entropy, it becomes several. Okay, but it bifurcates into several ones. So, for example, at least two usually appear: is the mean entropy and the max entropy. So here we have the mean conditional entropy. There exists some notion of max conditional entropy that I don't want to get into the details. And we actually need that because what we usually observe is that, this quantity that had like two different operation interpretations before, in the single shot case, each one of these operation interpretations correspond to one of these two, min or max. So for the entropy itself, which is easy, the max entropy we saw is compression, right? But asymptotically, the entropy, we can also see it as how much randomness we can extract from the state or from the probability distribution. This other operation interpretation actually goes to something that we call S min or H min. Okay? So we have to consider all these different entropies now. So this is the relevant one for our problem. We also have, well, as I mentioned, the max one. And actually there's a nice relation. The max one is related to the min one, up to, if you consider purification. So this is a definition of max if you want, okay? So we don't have an expression for max, but we just define the max entropy of A and C as minus the mean entropy of A and B, okay? So, and finally the mutual information. So what played the role of this mutual information here, we need something more complicated. So we need this guy here. So if this was all Shannon entropies or von Neumann entropies, we'll get entropy of A minus entropy of A given B. And this is equal to entropy of AB minus entropy of B. So you see we would get exactly the mutual information. So now we just have something like mutual information, but we put some max and some mins, okay?
What is psi ABC?
Sorry?
What's psi? Which state is psi ABC?
Psi? Oh, so you have a state on AC. You consider any purification on ABC that you want, okay? Doesn't matter what the purification is. Okay. So what to use in the proof, right? What were the information theory that we use in the proof? One was this entanglement distillation, right, that we saw the protocol. And one was this saturation of mutual information, which is a basic properties of entropies. And was, we got from Hastings. Now we only have one copy of the states. So we want to use this to see what it gives us, right? Okay, so now what are the analogs? Let me just show you. And I guess I will stop here in the technical parts and just mention some open problems, okay? But I just want to show you what are the actual things that we have to use in the proof. And once we have these things, we can sort of use the same procedure as before, okay? It's more work because they are less, they are not as nice quantities as von Neumann entropies, but you can still do it. So this was the result that we had before, right? Entropy of C bigger than entropy of P. It implies some bound on the correlations. Now we have to replace by two different results. So first, right, as I mentioned, we can write this as the minus von Neumann entropy of A given C, right? We saw this before. It's one way of rewriting this. So this is equal to HC minus HB, and HB equals to H of AC, because it's a purification. So this is the same thing as HC minus HAC being positive, and this is just the conditional entropy. Okay, so this is just a replacement as before, right? We just have something like conditional entropy being big, and now one of the things of single shot is that, whenever we need smoothing always, and then these smoothings, they start messing out the bounds. What was simply bigger than 0 before, now we need some constants and some factors that depends on the smoothing, okay? And then we have exactly as before. The correlations between A and C is bigger than some mutual information. But now the max mutual information that I showed you before, right? So this is pretty nice, right? This is just as before. And actually, how you prove this, you just use a single shot version entanglement distillation, okay? That's by these guys. We just use this. So this first relation is exactly as we derive, with this, as we did before. We just derive from entanglement distillation. So these are the rates now that we have to work, this and this. This is not enough, and we need some variant, another variant of this expression, right? So it has many variants now. And this is using max entropies, okay? So this says that if this is bigger than that, we have some implication. Now we have something that if for the max entropy of C is bigger than 3 times the max entropy of P, we need some slack here. Again, the correlations are upper bound by something, okay? As before, correlations of A and C, but now we have some other expression using H max, okay? Asymptotically, this will be a very, this will mean nothing because this will be much more loose than this one, simply because the mutual information of A and B is always smaller than twice the entropy of P. But single shot, things get more messy, right? So we need these two expressions, okay? So this is what just I mentioned. We can rewrite this as entropy of C minus entropy of AC. These two have the same entropy, B and AC. And this is minus the conditional entropy. Okay, so then this is what I mentioned. This follows from single shot merging in the same way as we did before. This is the EPR rates. Okay, let me stop with this. So we saw before this, this single shot merging is just entanglement distillation here. So we saw that the EPR rates was this, right, minus conditional entropy. So now we just change by minus max conditional entropy, plus some error terms, right? So this is nice analog. And the communication cost before was the mutual information. Now it's just the max mutual information, okay? So we have, it's pretty analog. And then this was proved in this paper. In this paper. And then, we have to go beyond. We have to use these other relations, but that doesn't matter. So I think that's a good point to stop. So let me just repeat that what we do is just, instead of using these results, we use these new results, and we try to follow the same thing we did before, okay? And you have to believe in that it works with more work. Right, so that's all that I wanted to say this technical part. So the last 5 minutes, let me just give you some overview, right, of what we saw. So, and let me tell you some open problems, okay, in which hopefully you think about them. So the topic was about area loss, right, which is something that comes from many-body physics or condensed matter physics, even before from like people studying black holes. And it's just some statement about the entropy of a subregion, or in a more modern view, about entanglement, right? We want to understand how entanglement scales in physical systems. And then we saw that it scales in an interesting way, right? Because it doesn't scale as the volume of the region, which we would expect in the case of random states, for example. It scales as the bound area of the region. So this is some expectation, and then what I show you is what we know about this expectation, what it doesn't, right? And then I show you that we understand it well in the case of non-zero temperature. For Gibbs states, area law always holds true in any dimension if you use the Newton information, right? But then I also mentioned that maybe that's the wrong way of looking at the problem, right? Because on one hand, it's very interesting because it tells us something about the scaling of correlations in physical systems, right? So at t bigger than 0, area law for the thermal states and the Newton information. Now, so this is very nice, but one thing that we saw is that area law in one dimension at least, zero temperature, it implies a lot about the states, right? We really know that the states is very simple. It's a matrix product states. We know nothing about this in this case. So one open problem is to try to find out what this gives us, right, in terms of approximation of the states. Can we get anything about the structure of the state from this area law? In one dimension, for example, it will be interesting already. And my expectation that it's not, but maybe there is something. And if it's really that you cannot get anything about this, then there is you should prove better area laws here, right? And one way to prove a better area law that I mentioned is to look at the purification of this guy and prove an area law for this purification. In one dimension, this is a consequence of this result I showed, but in high dimensions, we don't know, right? So it's an interesting open problem to try to prove area laws for thermal states in higher dimensions, constant temperature, but for the purification of the states. And then the area law is in terms of entropies, not of Newton information. Okay? Maybe this is so easy because it's not the right thing to do. This is one thing. Then we study temperature equals 0, right? And here, for one dimension, we see that we know many things, right? First, there was this original result by Hastings, proves area law whenever you have a gap on the Hamiltonian. So the ground state has an area law. And then what I show you in more detail is this result that it's enough to suppose that the ground state has a correlation length. That any state has a correlation length. Any state with a correlation length satisfy an area law. Okay? And then this works for degenerate ground states, or even for purification of thermal states, or for these systems with mobility gap that I mentioned. And the proof was using this information theory, right, like entanglement distillation. So now what's the biggest open problem in the area, I think, is what happens in 2 dimensions, right? So, or in higher dimensions, but 2 is already very interesting. So we don't know, right? We know this Hastings result by 6 years now, and so far no one could generalize the results to 2 dimensions. Either his proof, or this proof I presented, or some other recent proof that I also mentioned by Landau, Arad, Kitaev, and Vazirani. So, and another interesting question is, suppose we have an area law in 2 dimensions. What it gives us? We know in 1 dimension it gives us a lot, right? But in 2 dimensions, we don't know if it gives us anything. So, maybe what we need to prove in 2 dimensions is not area loss, but it's something more, like that there exists a good tensor network state. This is another interesting question, right? So what are the implications of area law in dimensions higher than 2? Okay, and with that, I think it's a good point to finish. So thank you very much for your attention during the 4 days. Okay, so I guess we want to go for lunch, but if anyone has a question, I'm happy to answer. If not, in the afternoon, yes.
The area law, you could have looked at through entanglement of formation. I know it will be monstrously difficult.
Oh, you mean here, for big states?
Will this
Right.
purification lead to something equivalent to looking at entanglement of formation?
No, so purification, this entanglement purification is something that people have studied in entanglement theory, right? It's called exactly entanglement purification. And it's not a measure of entanglement, it's a measure of correlations in the states, which is exactly what we want for proving, matrix product state approximations, for example. But your question is good, is an interesting one, because entanglement formation can be much bigger than mutual information, right? So we do not have an area law for entanglement formation, for example. And I think it will be interesting to see if there is some proof of thermal states for entanglement formation. It will be one step forward, right?
Why do you say it will be larger than?
We have states for which mutual information is much smaller than entanglement formation.
Yeah, but that can be the other way also.
Or it can be, yes, indeed. But what I'm saying is just that this area law doesn't imply anything for entanglement formation, right? It does imply for distillable entanglement, for example, but not for entanglement formation. So it's an interesting question to see what happens for entanglement formation. Oh, yes.
So more technical, the statement for the area law that you wrote down, was already yesterday or the day before, it had an exponential dependence on the correlation rate.
That's right. Oh, yeah, good.
So, and I guess it comes from this saturation lemma, right?
Yes.
You need it there.
Exactly.
But from Arad et al., we know that, at least assuming a gap,
That's right.
you get actually much better dependence.
That's true. Yeah.
So is there any hope to
Right.
improve, to get your proof also to
Yeah.
reach this kind of dependence?
Yeah, very good question. Yeah. So Andreas' question is that first we saw this original result by Hastings where the bound on the entropy is exponential in the correlation length. Then I mentioned this very recent result for which they get a bound which is proportional to the correlation length, right? Which makes sense physically, right? So it's very nice. Now the proof that I show you without this is when you have a gap. Now if you only have correlation length, nothing more about the states, the bound that I show you is exponential in the correlation length as well. So it's a very natural problem to try to improve this to something linear or at least polynomial in the correlation length. And the place where it happens is exactly in this saturation of mutual information, right? This is where we get this exponential dependence. So, it's interesting to see if we can improve this saturation of mutual information lemma. Perhaps using exponential decay of correlations, right? Perhaps when the correlations decay fast enough, we have a better version. So this is a nice open question related to the techniques that I show you. Okay, yes?
What are the results known in 2 dimensions? Maybe no general results.
What it's known? Yeah. Right. So first in 2 dimensions, there is this, you can call exactly solvable models. So you can construct many interesting models that satisfies the area law, but it's more by construction. And there is this theory of higher dimensional MPS states. They call PEP states. These guys always satisfies area law by construction, and you can construct interesting models that have them as ground states. Apart from that, the most general result in higher dimensions, which follows from this one, is that if you have in 2 dimensions some Hamiltonian with a gap, but now not only you know that there is a gap, you have some assumption about the density of states. Okay, so if you plot the energy of the eigenstates, then versus the number of them, the number of eigenstates, then of course, right, usually have something like this. And you're interested here, very close to the ground state. You want that this only grows, that n only grows as a polynomial in the energy. Okay, so something like this. So you don't have a lot of very low lying that generate ground states. If this is the case, you can use this result to get an area law for the ground state as well. Okay, so we don't know which class of models satisfies this. Like commuting models always satisfy this. That's another thing. For commuting models, where the terms of the Hamiltonian commute, you always have an area law, and it's a very simple proof. Okay, so we have in 2 cases, either commuting models or models where the density of states doesn't grow too fast, close to here. But it's an interesting problem to try to understand how rich is this class. Okay, so yes. Okay, so thank you, and let's go have lunch.
I know Fernando will be possibly here during the tutorial.
I will, yes.
But on behalf of all of you and on behalf of the Institute.
Thank you very much.
To come down here and spend so much time with us. And from your interactions with the participants, you know that you have really ignited a lot of interest in them.
Thank you.
And
Yeah.
as I told you yesterday, I hope you feel welcomed. And I also want to repeat that we would like you to visit us frequently, whether it happens to be your birthday or not.
Thank you. It was a pleasure. So thank you very much for staying until the end.